In this lesson, we'll dig into indexing specific document fields and configuring search behavior for each field. You'll learn how to store field data within the index and to control whether fields are searched by default or whether they require field scoping within your search terms. We'll look at some other things as well. As you already saw, it's completely possible to index all fields of all documents in a target bucket. It's the default behavior. The problem is, if you dynamically map and index all fields in your documents, your index will be huge. So you should only use this approach for those relatively rare use cases where your document fields continually change. Instead, you will normally index specific fields for each mapped document type. To do so, check Only Index Specified Fields in your type mapping. Otherwise, all child fields of this mapping will be indexed. Also, because it's completely valid to map multiple document types to be included in an index, you'll want to remember to uncheck the default mapping. Otherwise, you'll continue indexing all documents, regardless of type, even though you also added a type-specific mapping. You can index any specific field within your documents, whether top-level or nested. You just need to know the field names. A top-level field in your target document type would be assigned as a direct child of your type mapping. Just click the plus button to choose whether it's a child field, meaning a top-level field in the target document, or a child mapping, which would be the name of a top-level JSON array or object containing its own child fields. Similar to how the type mapping operates, if you add a child mapping, all of its own child fields will be indexed by default, unless you check the box to Only Index Specified Fields. If you do so, you will then add child fields to this child mapping and configure them individually. Each child field in your index is individually configured. You specify the name of this field in the target document type, as well as the data type of this field. You also set the name by which it should be searchable, which defaults to the name of the document, but can be changed here to something friendlier for field scoping purposes. Maybe you use some funny naming conventions in your documents. You can also choose whether to store this field data locally in the index, and if so, whether you should also include term vectors, position information about this term within its document, to support highlighting of the stored data in search results. Now, by default, all indexed fields are searched for every search term because these field names are included in what's called the all field, meaning what fields should be searched for each term, by default. However, you can disable this behavior. If you do, then this particular field will only be searched if its searchable name is prefixed to a search term. We'll walk you through this behavior in the lab ahead. If you wish to create an alternative version of an index, change it over time. You can clone its design, which would also clone the stored data in the underlying index. This will be particularly useful when you're evolving an index which you've deployed for use via an index alias. You can clone an existing index, modify it, and then swap the alias endpoint to the cloned modified index when it's ready. We'll look at this technique a bit more in a later lesson. So that's enough slideware for the moment. Let's jump into Couchbase to clone and modify an index using the techniques we've just learned. First, I want to go take a look at what I'm going to index. I'm going to go to my buckets. I'll go to beer sample and open the documents. We see that these documents have the word brewery, at least these first ones do, embedded in the document ID. Now if I edit that document, well, that's good. I see there's also an embedded type field. I could extract my document type using a regular expression here, but it sure is a lot easier to work with an embedded type field for the type identifier over in my search. Now what I want to do is index just the description field of my brewery documents. So I'll go over to my search screen. I'm going to go to this demo index we already created, and I'll clone it. I'll modify the name to be CB121 Demo 2, also for the beer sample bucket, and notice that I'm defaulting to expecting a JSON type field named type in my documents. I know I have that. Now I'm going to add a type mapping. So I'm mapping for documents that have the word brewery in that type field. I only want to index specified fields within those documents though. Okay? But which field do I want to index? Well, here's the plus button for that type mapping, and I have a child field within my brewery documents called description. Description is the data type text. We'll play with the others later. And because I'm going to leave it included in the all field, I don't need to worry about the searchable as name here. I'll go ahead and OK this child field, and then I want to remember to uncheck the default type mapping. Otherwise, I'd be indexing all of my documents, not just the brewery documents, and I'd be indexing all fields in all documents as well. I'll go ahead and create this index, and once the indexing progress is at 100%, I'll go in and search for the phrase grilled cuisine. When I search, I get some documents back. I'll click through to my first document and see that yes, the phrase grilled cuisine does appear in the description of this brewery typed document. Of course, there's a lot more we could do here, and you'll be seeing more ahead. So let's talk a little bit more about storing fields in an index. As we just saw, by default, all you get back from a search is a set of document keys, albeit in descending order by term score. What this means, though, is that you would need to make a second request to get the document itself, which may be fine. But you can also choose to store field data directly in the index for faster access. You get these results with no second request. And optionally, you could also include term vectors in the results, which, as you'll see later when we get into JSON-based requests, is expressed as tagging around the search terms in the stored results. You might choose to highlight those tags in your output, as you see happen in the default output in the UI here. Now, the downside to this approach is that you do increase the total size of your index by including all this extra field data. You'll choose what's best here based on your use cases. Now, in the previous lesson, we pointed out how indexes are defined as JSON and can be modified via REST API. If you wanted to do so, notice here that you can copy not only the definition, but also a pre-generated curl command for doing so, directly from the UI. Now, in the next lesson, you'll see similar behavior in relation to individual queries, and we'll be using that to drive our JSON and REST-based work in the labs ahead. So what have you learned here? Well, dynamic indexes are probably too big for production use, unless your documents have unpredictable structure and variable field names. Normally, specific fields should be indexed for each document type. Now, these may be a top-level field of the indexed document type, or you may require a mapping to reach the field or fields to be indexed within a nested array or object in your JSON. Each field to be indexed is configured as to its name, data type, searchable name, whether its data should be stored, whether term vectors should be included with stored data, and whether or not field scoping is required based on whether or not that field name is included in the all field. There's more as well. We also saw that you can clone indexes, which is helpful when updating from behind an alias. In this lab, you're going to play with stored field data a bit. You'll also index nested fields and search specific fields via field scoping of your search terms, all going a bit beyond what we saw here on the slides. I hope you take a few minutes to work through and learn some of this by hand. When you're done with that, though, come on back. We've got a lot more to cover.